All right, so let's go ahead and get started. This is Rithik, and I'll be talking about the traveling salesperson problem and the Christofides algorithm. Okay, so let's get started. What is the traveling salesperson problem? It's an extremely well-known problem in the field of graph and optimization theory. The problem, it's simply defined as a scenario where you are a traveling salesperson and you must start in your hometown. You have to visit every city exactly once and return back home in the least amount of time as possible. We represent this problem as a connected and undirected graph, where each edge is considered a path from one city to another, where the cities would be the vertices. So essentially, the task is to find the shortest Hamiltonian cycle, starting at your hometown. Now, despite this problem being, seemingly common and, simple to explain, finding the optimal solution is actually NP hard, which means it cannot be guaranteed optimally in polynomial time. So there's two important considerations kind of before we dive headfirst into the problem. The first is that the weight of edges must satisfy the triangle inequality. In other words, like we learned in class, distance has to be a valid metric. This is important because it'll ensure that later on, when I explain the Christofides algorithm, that shortcutting a path will never increase the total distance from one vertex to another. Now, this is shown pretty clearly in the example on the right, where the path from 2 straight to 6 will always be shorter than if we went to some other vertex, like let's say 5, between 2 and 6. So 2 to 6 is always shorter than 2, 5, 6. The other prerequisite is the symmetry property. Now, this is a pretty simple one. It's kind of already assumed when we say that we're using an undirected graph, but it just means that the weight while traveling in either direction along an edge will be the same. So you could think of that as a two-way street. So why is it NP hard? Now, TSP is NP hard because while we can detect an Eulerian circuit by simply observing the graph has, only even degree vertices, detecting a Hamiltonian cycle itself is an NP complete problem. So it takes much more computation. Every time we travel to a new city, there's one less option to choose from for the next city we travel to. That suggests that since we have to start with one of the other cities, this will take n minus 1 factorial time simply just to find these paths. And it turns out actually that given a tour, we actually can replicate that tour by reversing the order of the cities in the tour. So basically going backwards, which actually means that the amount of time we get is n minus 1 factorial over 2 to search through all permutations. And as you can see in the image, even with just 20 cities, this is not by any means a practical solution, especially since any real application will likely have at the very least hundreds or even thousands of cities or destinations in a given route or solution. So clearly, we need to have some sort of approximation algorithm that can give us a solution that maybe isn't optimal, but has a good enough guarantee and is fast enough for us to rely on it. Okay, so before we dive into the Christofides algorithm, which is known to be the best approximation algorithm for TSP, there's a few important concepts I just want to briefly mention that will require before we can understand the algorithm. So these concepts are all stuff that we've talked about, discussed in class. So I'll just really quickly reiterate. First, we have minimum spanning trees. Now we use these for Kruskal's algorithm to find shortest path from one vertex to any other vertex. Second, we have the handshaking theorem and the concept of even and odd degree vertices. And third, we have perfect matchings. If you aren't totally familiar with perfect matchings, the image on the right here is a good example. A perfect matching is a matching where every vertex in the graph is incident to exactly one edge in the matching. You can see that in these 9 perfect matchings on the right, each vertex is only incident to one edge, and every vertex is part of an edge in the matching. And lastly, it's important to know that Eulerian graphs, which are connected graphs with only even degree vertices, always have an Eulerian circuit, which is a path that visits every edge exactly once and ends at the starting vertex. A Hamiltonian cycle, which is what we're looking for in this problem, is similar, but it visits every vertex exactly once and ends on the same vertex. So Eulerian circuit goes through all the edges, and a Hamiltonian cycle goes through all the vertices. As I mentioned before, there is no simple trick for detecting a Hamiltonian cycle, even though there is one for Eulerian circuits, which is pretty much the main reason that this problem is NP hard to begin with. Okay, so the Christofides algorithm, which I have here on the slide now, it's the most well-known and reliable algorithm, as I've said, for finding a reasonable solution for this problem. There's 6 steps, and here I'll walk you through them. So the first step is just to simply compute a minimum spanning tree starting from your defined starting point, so wherever your hometown is in this scenario. We do this because interestingly enough, as you can see in this image on the left, minimum spanning trees often share many edges with the true optimal TSP, which in the future I may refer to as, OPT or optimal solution. The second step is then to find the set of all odd degree vertices in the resultant minimum spanning tree. So in that minimum spanning tree you just generated, find all of the odd vertices, odd degree vertices. This will then help us to set up the perfect matching so we can construct an Eulerian graph, which we'll talk about in the next slide. Okay, so now we'll find a minimum weight perfect matching on our set of odd degree vertices that we got from the minimum spanning tree. As shown on the image, we'll then combine the minimum spanning tree and the perfect matching's edges to construct an Eulerian graph. Since the perfect matchings are only between odd degree vertices and each vertex in a perfect matching is only incident to one edge, this means that all the odd degree vertices will increase in degree by just one, and they'll become even degree vertices. Resulting from this, we know that our constructed graph is Eulerian because now all the vertices are of even degree. Okay, and now we'll find the Eulerian circuit since we know that every Eulerian graph has an Eulerian circuit. The image on the left shows an Eulerian circuit starting and ending on 0. The image on the right represents our final step, which would be to shortcut the vertices that are repeated in the Eulerian circuit. Now, since we know our weights are a metric and satisfy the triangle inequality, we know that this will not increase the overall path length. So every time we reach a repeated vertex, we skip over it to the next unvisited vertex that we have in the Eulerian circuit to then ultimately construct a Hamiltonian cycle starting and ending on the same vertex. And as you can see on the right, in the bottom of the image, we've kind of skipped over 11 and then we skipped over 6 and 12 because we'd already visited those previously. And we just continue, so we go straight from 3 to 1 because we skip over 6 and 12 near the end. This gives us our resulting solution to this problem, and now we'll discuss the efficiency of the approximation algorithm. Okay, so the three halves approximation, it's the idea that the Christofides algorithm will always find a solution with weight that's at most 1.5 times the weight of the true optimal solution given the bounds of this specific instance of this problem. And here I'll do a quick breakdown of why we understand this. So since the minimum spanning tree is defined as the lowest weight possible, but it isn't a cycle, it is the ultimate lower bound for the OPT, and therefore must be less than or equal to our optimal solution. Since the optimal solution visits odd degree vertices in pairs around the circle, this naturally defines our perfect matching using every other edge. That matching uses exactly half the edges of the optimal solution, and since Christofides picks the lightest possible matching, so the lowest weight, its cost can be no more than that. So that's how we get the 0.5 of the optimal solution for the weight of the matching. So when we put these together, since we have to do both of these every time we construct the Eulerian graph, we'll get that the upper bound for the Christofides algorithm is just 1.5 times the optimal solution at most. Okay, so summing everything up, there's a few important takeaways from this problem and from the approximation algorithm. Firstly, sometimes when we find a true optimal solution, it's simply unreasonable. Like we saw the n minus 1 factorial over 2 runtime for that. It's just unreasonable for even 20 cities. Thankfully, we have approximation algorithms, such as Christofides, that can help us find reasonable solutions to even problems that have NP hard difficulty. And finally, it's clear that just putting together like a few of the core concepts that we learned from this class, so stuff like the handshaking theorem and spanning trees, we can actually come up with state-of-the-art algorithms that solve, I mean, a pretty important problem and a problem, a solution that's been around and has been best for almost 40 years now. So, okay, that's all for the video. Before I end, I just do want to give credit to Reducible on YouTube. Like all the images with purple backgrounds I pulled from one of his videos, and they were very helpful. But yeah, that's all.